As we move on from the mixer, of course there's no afterburner in this engine, so it's nice we can say that TT6, our temperature going into the or out of the afterburner, is going to be equal to TT 5.5, and also that PT6 is going to equal PT 5.5. So that really means next up we just have to worry about what's going on in the nozzle. And in order to get a little more of a clue there, we actually have to jump way back to the beginning here and read our key text, where it says that we've got the nozzle is variable and converging diverging. And in lieu of any additional information, we're going to assume that the nozzle area is varied, the nozzle shape is varied, to make sure that the exit pressure matches the ambient pressure. It's not an absolute requirement, but if it's not stated otherwise, we're going to be assuming that if it's a variable area nozzle, you're adjusting to make exit pressure match ambient pressure. So we know that P8 at the exit of our combined nozzle is going to be equal to PA, our ambient pressure. And so the other thing we know is, since that area is varying, we don't need to check for choking. It's set up so that P8 and PA are equal. There's no question about the flow being choked, so we don't have to do that check today. And we also know that that means we can calculate, and since it's an adiabatic nozzle, we can also say that TT6 is going to equal TT8. And based on that, we can calculate that the ideal static temperature at the exit is going to be equal to the total temperature at the inlet to the nozzle, TT6, times the static pressure at the exit over PT6 to the gamma minus 1 over gamma. And this is one area, again, where our variable properties, there's a little bit of inconsistency. In the book it mentions that if we're going to use a gamma here in the nozzle, that we would evaluate the average of TT6 and T8. But when they actually do their problems, they're just always evaluating it using just TT6. So obviously the more accurate answer is to do the average value, but here, just for being consistent with the other book examples, we're going to use just TT6, which knocks off the iteration problem here, because we already know TT6, and we can then evaluate our appropriate value of gamma, and we don't have to worry about iteration on this step to deal with for those air properties. So we can solve directly for our ideal static temperature here, and then we can use our nozzle efficiency, eta n, which is defined as TT6 minus the real discharge temperature over TT6 minus the ideal discharge temperature, and then we can reorganize that to solve for the actual discharge temperature of our nozzle, T8, which will be equal to TT6 minus eta n times TT6 minus T8 prime. Substituting numbers into these equations, we can solve to find that our ideal exit static temperature is going to be equal to, again, TT6, which is 796.218 degrees Rankine, times the pressure, total to static pressure, static to total, really, pressure ratio, where the static pressure P8 must match ambient, so it's 2.99 psia divided by PT6, which we just found to be 9.541 psia. It's all going to be raised to our gamma based off of TT6 here. So we're going to have 1.388 minus 1 over 1.388. And that's going to give us a new ideal temperature of 574.94 degrees Rankine. And then we can calculate our real temperature based on TT6, which again is 796.218 degrees Rankine, minus our nozzle efficiency, which was given to us as 0.95, times, again, our total temperature at 796.218, degrees Rankine minus our ideal total temperature, ideal static temperature, 574.94 degrees Rankine. And so from that we'll get an exit static temperature of 586.005 degrees Rankine. We can carry on from there to calculate our exit velocity of the nozzle, U8, which is going to be equal to 2 times the appropriate specific heat times TT6 minus T8. And we can throw in the whole thing under a square root there. And so if we put in, again, our numbers, we're going to have 2 times the specific heat based on TT6, so it will be 0.24273 BTUs per pound mass degrees Rankine, and that'll be times our temperature difference of TT6, which is 796.218 degrees Rankine, minus our static temperature we just calculated, 586.005 degrees Rankine. And there we also will need to make a conversion. So we have units in BTUs, we have them all over the place. So we'll have, first we'll get our BTUs into foot-pounds of force. So we know there's going to be 778.16 foot-pounds force per 1 BTU. And then we also know that basically we'll have 32.17 pounds mass feet per second squared per 1 pound of force. And of course this all is under the square root. And so just checking our units here, of course the degrees Rankine will cancel out. Our BTUs are going to cancel out. We get rid of our pounds force here, and we're going to be left with, and we're also getting rid of our pounds mass. So we'll be left with, again, feet squared per second squared, which is what we want. So that'll give us our U8 is equal to 1602 feet per second.